All right. So this is a big problem. We don't have exponentially large computers. And it's an even bigger problem when we're talking about two nucleon systems compared to single nucleon systems for more than just the fact that the noise scales exponentially with the number of nucleons in the system, but also because we're interested in looking at scattering. And as we hopefully know by now, scattering involves looking at tiny energy differences due to interactions compared to the energies. So the thing that goes into Lucier, that this zeta function, is delta E, right? So this is the thing that tells us about the interaction. It's the energy of the two nucleon system minus twice the energy of the single nucleon system, or rather twice the mass of the nucleon. So while the mass of the nucleon is of order a GeV, these energy splittings are going to be orders of magnitude smaller than that. We're talking on the order of maybe 100 MeV, something like that. And if you think about this zeta function, so this S function that we plug our energies into in order to get peak cotangent delta, so that's plotted here as a function of the argument. And we know that it has these poles at the non-interacting energies. So these guys, I should have chosen blue, that's okay. So there are poles everywhere, every time you go through a non-interacting energy, because when the particles are non-interacting, we know P cotangent delta, oh, I'm in the wrong thing, hang on. So P cotangent delta goes like minus 1 over A plus dot, dot, dot. And when A goes to 0, that means you have no interaction. When A goes to infinity, that means you saturate unitarity. So when A goes to 0, P cotangent delta goes to infinity. And that's why we have these poles at the non-interacting levels. And it's the difference between, it's the distance from the non-interacting pole to the energy level that you extract that tells you about the interaction. So here, these are some effective masses of actual energy levels versus time. And the dashed lines are the non-interacting two nucleon levels. And the thing we're trying to extract is this tiny distance here. I can't even draw that small on my screen. So it's the distance from the non-interacting energy to the energy we're trying to extract. And so now you can understand why, if your error bars are exponentially growing, this is a really big problem, because you're never going to be able to resolve these tiny energy differences if you have noise on top of that. You can also we'll talk a lot about operators and how we can try to correctly diagonalize these correlation functions to get good energy levels. You can do a really bad job, and essentially you're not going to see any signal at all because the noise has swamped your signal before you can ever reach it. Okay, but we'll talk about operators next time. So the next thing I want to talk about are, oh, I'm in blue, so-called false plateaus, fake plateau, mirror plateaus. There are lots of different names in the literature for these. So what is that? So you'll notice that this data here is not positive definite. So it can go up, it can go down, and it can approach the ground state from any direction. And this is symptomatic let's just say non-positive data of non-positive data. So what's the issue here? The issue is if all of the terms from your correlation function, so recall C of t looks like this. If you have a positive definite correlation function, then all of your overlap factors are positive, and each term is therefore positive. And this means that the energy must be approached from above, because as more and more of these terms become important, so let's say you're starting at late time and you're going to early time. So at late time, only this one dominates, so it's going to be positive. And if we go to earlier and earlier time, we're going to add more and more of these terms, but each term is positive. So going to earlier times is just going to increase the value of your correlation function. So it has to approach the ground state from above. If you don't have positive data, then you can have near cancellation of these terms that results in something that looks like a plateau, but is in reality just a local min or max, okay? If your correlation function is positive definite, there are no local minima or maxima. But I'm going to show you some fake data. Let's see. This guy. Okay. So here is an example. I have produced some fake data by just writing down something like this and plugging in numbers for A, E naught, B, E1, etc. And I've allowed the A, B, C coefficients to be different in sign. And so if I just look at the data, it looks like it might be plateauing. Well, I don't have the right-hand figure here, but it's plateauing to a number about maybe 0.97 or 8 here. Now, okay, however, let's see, how did I grab this? There we go. If I go out later in time, I'll see that what looked like it may have been a plateau around 10 was in fact just a local minimum. And if I continue to go out, it very, very slowly approaches the true ground state, which I input to be 1. And you might say, well, I wouldn't be fooled by this. You can see, if you look really carefully, that it actually is very, very slowly rising after 10. So this isn't the true minimum, and no, I wouldn't be fooled by this. However, remember that we have noisy data. So that same data, if I add this exponentially growing noise, completely washes out any trend that you might see. And so if you were to fit this, let's see, right? If you were to fit this to, say, a couple exponentials starting around here, it would look like it flattened out. That was a terrible drawing. Here, it flattens out. And your error bar would be dominated by these early time slices here, right? So the error it would give you would be maybe something like this. Because if you add more and more late time data that has these big error bars, it really does nothing to your fit at all. The fit and the error will be largely dominated by these early precise results. And so you can be fooled if you have noisy data. And of course, if you said, okay, well then I'll just have to go to very, very late time where it's actually plateaued, no, you're never going to see it because your error bars are going exponentially. It's actually even way worse than this toy data. I have a very slow growth of error bars here. We'll look at some actual 2-nucleon data, but what you see is essentially you go from having something you can extract to just zero, just garbage. Okay, so let's see. I have another question at this point, so I will go ahead and stop this video.